Hi, welcome back to Circuits with Angel. Today we will be calculating Ohm's law in a parallel circuit. We already did a series version and I said I'd make a parallel circuit one. This took a while for me to learn and make, so here we go. We will be examining and going through a 3-branch circuit and going through each branch in it. This video will be like my series circuit video. If you haven't already watched that, I strongly suggest you do so, because I will be talking a bit about things from that video. We will also need a multimeter to measure things, so go watch that video because I go over how to properly use a multimeter and its settings. Okay, I know this is a lot of videos to watch, but it's needed to understand what I'm presenting. There's only one more. You need to go watch the Ohm's law video so you understand the basics of the formulas we're using in this video. I have the links for all of these in the description so you don't have to spend too long looking for them. Our constant values in a parallel circuit are voltage, V equals constant in all parts of the circuit, current adds up to a total, I adds among branches. Resistance, resistance equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Now remember, from the last video, I talked about the importance of doing this along with me, and I will remind you about it. If you do not do this experiment along with me and think watching is okay and you'll learn the same thing, you won't. There is a difference in the things you will learn by watching and by doing. This video is made to have you build and fill out the worksheets in real life. Well, now that we know that, we can go learn the parts we need for this experiment. First in this experiment, we will need one breadboard, one 470 ohm resistor, one 5.1 k ohm resistor, one 6.8 k ohm resistor, one 6-volt battery pack with preferably new batteries, but they don't have to be, 6 Solidcore Jumperwires, 2 Alligator Clips, 2 Multimeter Leads, and 1 multimeter. We can now move on to measuring the voltage in our battery pack, which is our first constant. The first step to measuring our voltage is plugging in the ports to the multimeter. So we need to plug in common and general testing port. Then we take the alligator clips and clamp them onto the multimeter leads. Black goes to black and red goes to red. And now we clamp our alligator clips onto our battery pack's leads. Red goes to positive and black goes to negative. After we finish doing that, we're going to turn the dial on the multimeter to 20 volts. And after we do that, we're going to wait a while to make sure we get an accurate reading on the battery pack's voltage. You can wait however long you want, but you should at least wait 10 seconds. I have waited a bit longer off camera, and the multimeter has settled at this, 6.29 volts or 6.30 volts. I'm going to write down 6.30 volts because it stays at that longer. And since voltage is constant in all parts of the circuit, we're going to write our voltage down in each one of the voltage squares. I could have wrote 6.3 volts, but I would like to write down what my multimeter told me, so I put in the extra 0 over there. Which, again, I could have not, but I'd like to be really accurate with this sheet. Now we move on to measuring our resistors, because that's another constant we must figure out if we want our calculations of the amperage to be correct. Oh no. It appears I have forgotten in the parts you need section that you need 2 Strandedcore Male Jumperwires. So you're going to need those. Right now I'm sorting out the resistors. R1 is 470 ohm, R2 is at 5.1 k ohm, and R3 is 6.8 kΩ. Now I'm going to put the 470 ohm resistor in the breadboard, and we're going to make a handy dandy testing board, which if you don't know what that is, you will soon see. But first we must plug in our ports, because I unplugged them from last time. They go to common and general testing port. Now we clamp our alligator clips to our multimeter leads. Red goes to red and black goes to black, or whatever color. I just chose black and red for my alligator clip colors because it was easier to remember what polarity each was. And now we take our alligator clips and we clamp them onto our male-to-male jumper wires. And after we clamp them onto our male-to-male jumper wires, we plug the male-to-male jumper wires into the breadboard on either side of the resistor, making sure that the jump wires are in the same row as the resistor, or else the multimeter won't measure anything. And now let's actually measure. We turn our dial to the lowest setting in resistance, and we're going to turn it up if it says 1, which means the value is too high for this setting, like it's doing now. And now we wait a while, like around 5-10 seconds, to make sure this is an accurate value of this 470 ohm resistor, and we're going to write it down. We're going to take out our 454 ohm resistor, put it in its box, and now we can go get our 5.1 k ohm resistor and put it right where the other resistor used to be in the breadboard, making sure it's in the same row as the male-to-male jumper wires, or else the multimeter will not measure it. Just wait a minute, it won't take as long as last time because we don't have to set up a multimeter. Now let's look at the multimeter. My multimeter says this setting is too low for its value, so we're going to turn up one more. I have waited a good 15 seconds, so it should be good. It's settled at 5.05 k ohms, which would be 5,050 ohms. Oh, and we have to write down ohms too, because we calculate in ohms. And now that we've got that one done, we're going to take our 6.8 ohm resistor and we're going to put it right where that other resistor was, remembering to make sure that the male-to-male jumper wires are in the same row as your resistor. No, it is at 6.72 k ohms. We're just going to wait a while. Yeah, it's 6.72 k ohms, which in ohms would be 6,720 ohms. And we can write that down, and we will be done with resistance. We're just going to put that at 6.72 k ohm back, and we're going to find out the total resistance, because, well, we have to write that down too. As you saw in the beginning, where I showed you my resistance card, the formula is kind of hard, but the sooner we get over this math, the better. So once we finish, you'll be wondering, why is the total resistance in a parallel circuit smaller than any of the resistors in the actual circuit? Well, it's because in a parallel circuit, the total resistance is an average of all the resistors put together. In a series circuit, it's different. You add all the values up together for a total. And so, we're just going to move straight on to calculating. If you remember the formula, resistance total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So we're going to start with 1 divided by resistor 1. So we're going to take 1 and divide it by 454. And that equals 0.002. You're going to want to write that down on some paper to remember it. Alright, now we can move on to 1 divided by resistor 2. That would be 1 divided by 5,050, which equals an exponential. I can tell by the E at the end. Well, luckily I have a quick and easy way to fix this. I took the first 3 digits of that, and we're going to times that by 0.0001, which is around the value the exponential would be, and we end up with 0.0001 because that's all I'm willing to add up. And we're going to move on to 1 divided by resistor 3. That would be 1 divided by 6,720, which also ended in exponential. Times that by 0.0001, and again we get 0.001, and we're going to write that down like the other numbers, and we can now divide 1 by all of those put together. So we're going to take 0.002 plus 0.0001 plus 0.001, and that equals 0.0022. Now we're going to divide 1 by that. So 1 divided by 0.0022 equals 454.54 ohms. We're going to just write that down, and resistance is actually done. Hooray! After we write that, we can go on to finding our amperage, or current. But before we find our current, we have to build our circuit so we can test if our calculations are actually correct. We don't have any LEDs in this circuit, just jumper wires and resistors. I have taken out the 6 Solidcore jump wires, so you might want to do that. Right now I'm going to be taking our 454 ohm resistor and put it around the top of the breadboard from negative rail to an empty row. I have exact coordinates on the breadboard if you want to follow it exactly, but you don't really have to. And while I was talking, I took our 5.05k ohm resistor and I put it a bit down on the breadboard from the negative row to an empty rail on the breadboard. And of course I did it again with the 6.72k ohm resistor. I put it below from the negative rail to another empty row. Okay, now we take one of our 6 Solidcore jump wires. We put it from the first resistor's empty row to another empty row on the other side of the breadboard. And we're going to do that for resistor 2 too. Remember to make sure that the resistor is connected to the Solidcore jumper wire, or else the circuit will not work and you'll probably not know why. So make sure. We're also going to put the Solidcore jumper wire at resistor 3. Now we get to use the rest of the Solidcore jumper wires. We're going to take the first one and put it from this jumper wires row into the positive rail. We're going to do that for resistor 2 too. We take it from this jumper wire into the positive rail. And of course, we're going to do that for resistor 3. We're going to take it from this jumper wires row into the positive rail. Now it's time to plug in power. And if you were wondering why we have 2 Solidcore jumper wires and no LEDs, it's because LEDs are a load and it messes up the calculations of this Ohm's law circuit. I will be making a video on how to calculate parallel circuits with loads, but I thought it was a bit too much for one video right now. But now we have to calculate the current after we measure it. Yeah, so we need to measure it with our multimeter, and the ports go to common and milliamps. I always take apart my multimeter setup just because I want to show you how to set it up from scratch. And clamp your alligator clips to your multimeter leads. Red goes to red, black goes to black, or whatever color to whatever color. But we now need to get our male-to-male Strandedcore Jumperwires, which are somewhere around the table. And we're going to clamp those to the alligator clips. And after we do that, we take out a Solidcore Jumperwire in the breadboard, and we replace it with our male-to-male Jumperwires. And now we move our dial to the 200 milliamp setting. The reading shows up as negative, so we're going to have to change our male-to-male Jumperwires around, and it should read properly. It says 13 milliamps. We can now go calculate what it's actually supposed to be. So current or amperage is voltage divided by resistance. So for amperage 1, we take 6.30 volts and we divide it by 454 ohms, and that gets us 0.013 amps, or 13 milliamps. Wow, we did our previous measurements correct. Yay! We can write that down now. 0.013 amps, or 3 milliamps. Now we can go find the other two values and calculate. We're going to take out those male-to-male Jumperwires, put back in the Solidcore Jumperwire, take our other Solidcore Jumperwire out, and we're going to put our male-to-male Jumperwires back in, and we should get our reading. It appears to be 1 milliamp or 1.1 milliamp. We're just going to go with 1 milliamp. Now we're back at our calculator, figuring out what it actually should be, which is probably going to be 1 milliamp. And then we start again with the math. 6.30 divided by 5,050 equals 0.001 amp, or 1 milliamp. That's really good. We really are correct in our measurements before. Now we're going to write that down. 1 milliamp, or 0.001 amp. And we can move on to our next value. We take our male-to-male Jumperwires out. We put the Solidcore Jumperwire back in, which is a bit of a challenge sometimes. We take our other Solidcore Jumperwire out. We put the male-to-male Jumperwires back in, and here's our value. It's almost 1 milliamp, but not quite. It is 0.8 of a milliamp. Well, let's get calculating and see how that turns out. So 6.30 divided by 6,720 is 0.0009 of an amp. So that would be 0.9 milliamps. Wow, almost spot on. We're just going to write that down. 0.9 milliamps, or 0.0009 amps. And now we go on to finding the total current or amperage. To find the total current or amperage, we have to add all of our milliamps together in their amps form. So 0.013 plus 0.001 plus 0.00009 equals 0.0149, or 14.9 milliamps. All right, so we can just write that down. 14.9 milliamps, or 0.0149 0.0149 amps. After this, we will be done our worksheet and it will be over. All we have left is an explanation about why we did this. Okay, so why did we learn this? This is important to know because there are different types of circuits with different advantages and disadvantages. Like a series circuit uses less current than a parallel circuit, but it's like one of those old Christmas lights where one breaks and the entire thing breaks. Well, that's just because it was probably built in series back then. But in parallel, if one breaks, the other components just do not care and continue working. And now we have our 3 points for today. 1. Voltage is constant in a parallel circuit. V equals constant in all parts of the circuit. 2. Current adds up to a total in the circuit. I equals I1 plus I2 plus I3. 3. Resistance is an average of all the resistors put together. R equals 1 divided by 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. That is all. Thank you for watching and see you next time.